Hi everybody, welcome to our second lecture. Just a quick administrative announcement. I posted the homework yesterday. I will try to post the quiz as well today. But definitely take a look at the homework, download Jump, let me know if you have any issues. I'm happy to walk you through those issues if you reach out via email or schedule an office hours or post on Canvas if you'd like your peers to respond. So today we're going to start talking about descriptive statistics. We're going to go through three measures of spread and three measures of center and three metrics on spread. So this is just an image trying to explain why you might want to use descriptive statistics. If somebody were to share their data with you, and this happens a lot over at SAGE, which is a statistical consulting group here at Virginia Tech that a lot of grad students and even undergrads use for help with research. When data is presented in this format, just close to its rawest format, it can be overwhelming, and we want to make things simple, especially if we have a point to make. So that's sort of the idea behind descriptive statistics. You don't have to use them on every variable or every column, but you should try to summarize the key points in your data by choosing the appropriate statistic that gets at those points. And we'll go through some examples of what descriptive statistics are and which ones you might want to use to emphasize different points. So first, I want you to take a minute, just from what you know so far, what do you think a definition for descriptive statistics might be? And do you have any examples of a descriptive statistic? Okay, so again here, I'm going to split this into two sections, the difference between descriptive statistics and inferential statistics, to highlight the differences between the two. Descriptive statistics are specifically about your sample, the data that you've collected. Inferential statistics are also derived from your sample data, but they're speaking to the population. They're making inferences from your sample to the population, like that image we reviewed last class. So here are some examples of some descriptive statistics that you may be familiar with: mean, median, mode. Another set of examples would be variance, standard deviation, and range. And I want you to take some time to think about what each of those two set of examples have in common within the set. So what do mean, median, and mode have in common? And what do variance, standard deviation, and range have in common? And then before we go to the next slide, I wanted to give you some examples of inferential statistics. No worries if you're less familiar with these. We will get into these in future lectures. Some of you may have heard of confidence intervals. There's also many test statistics, which are often used to detect differences. So you might have heard of like a t-statistic, z, f, or chi-squared statistic. And again, we'll be covering those in future lectures, so no worry if that sounds like gibberish right now. So back to the original question, what do those sets of examples have in common? Well, the first set, mean, median, and mode, are all measures of center. They're all getting at where's the center of my data. And there's different definitions and interpretations of what that center is, and different statistics getting at that center. So we're going to talk about each of those three, what they mean, and then we'll get into which ones you might use when. So mean is also known as the average, as I said before, and there's a lot of synonyms in statistics. And it's very easy to calculate. You sum up all your data points and divide by the number of observations. You can only do this for quantitative data, right? It doesn't make sense to sum up data like gender. And we'll talk about more about the difference between quantitative and qualitative data in our next lecture. But in short, quantitative data is numerical and qualitative data tends to be categorical, meaning categories or text. So one interesting thing about the mean is that it's the center of mass, and what that means is that if you were to plot the distribution of your data, which is something we're going to cover later in this lecture, but I'm sure you've seen a density plot or a histogram before. It's the mean is the point at which if you were to balance the data, it would be perfectly balanced. So we'll have an example that covers this in more detail, but that's an interesting fact about the mean. As far as how it's written in mathematical notation, you could write it as x bar or as mu, depending on the context. So I'm going to ask you, what do I mean when I say depending on the context? When would you write x bar and when would you write mu? And I left you a little clue of an image you may have seen or seems familiar from our previous lecture. So you refer to the data, the mean, as x bar when you're talking about your sample mean. So when you're calculating it from your sample data, the mean is also known as x bar. However, your population mean, meaning the true mean, if you were to somehow magically get all of your data and calculate the mean as the sum divided by the count, is mu, the Greek letter mu. So again, they're both means, but there's a huge difference in interpretation between the sample mean and the population mean, which we'll get into when we start talking about inferential statistics. And just to know, I want you to know some mathematical notation, although this class is going to be pretty light on that notation. The median is probably really intuitive, especially if you're familiar with Spanish. Literally means the middle. And how do you define the middle? We talked about the mean being the center of mass. It's a type of middle. But in this case, when we say middle, we mean order your data from smallest to largest and pick the one in the middle. Now I'm going to ask you, what do you do in the event of a tie? So let's say you have an even number of data points. We'll make it really easy and say just 2 data points. How would you find the median? So hopefully you had the intuition to say you would just take the mean of those 2 data points. Just add them up, divide by 2, and that's your median. So there's a little bit of overlap between the mean and the median in the event you have an even number of data points, right? If you have an odd number of data points, there will be one number in the middle with an equal number on each side, and there's no math that you need to do after ordering your data, except counting to get to the middle. But if there's a tie, you're essentially taking the mean of those 2 numbers that are tied. The mode I like to remember starts with MO. It's the most popular value. So another measure of center, to go back to our analogy or our example from the previous lecture, sometimes in some forms of elections, people are interested in the mode just because there's a lot of categories and we want to know what the most popular data point is. But even for numeric data, you can use the mode, assuming it's discrete and you have more than one observation for each number. Or you could say there's no mode in the event that you don't. And I know I just threw some big words out there. All I mean when I say discrete, which again we're going to get into next lecture, is it's an integer number, a whole number without a fraction or a decimal appended. So yeah, mode is typically used for categorical data, but you can use it for numeric data, assuming you do have some amount of data points that repeat. So here's an example of calculating measures of center. So I want you to look at example A to start and tell me what the mean, median, and mode of that data set are. Ignore the spacing, it's not relevant right now. I'll get into why I put a space there later. And then for example B, I want you to also identify the mean, median, and mode. There's no numbers, but just take a guess as to where those values might lie. All right, so let's go through A first. So the median, if you remember, you order your data, there should be an equal number of points on each side. And as you can see, that is 6 because you have 4 data points on each side. The mean you might have remembered as the measure of center. In this case, you didn't actually have to add them all up. I gave you a little clue. It's perfectly balanced. I told you it's the center of mass, and it's perfectly balanced at the number 5. If you did add them all up and divide by the number of data points, you would have gotten 5 as well. These numbers add up to 45 if I did the math correctly, if I did the arithmetic right. And when you divide by 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, you will get 5 for your mean. The mode, on the other hand, is 7 because it appears 3 times. In the other example, your mean, median, and mode are exactly the same. It's the center of mass, the most popular data point, and in the middle if you were to order all your data. And we'll talk a little bit more about this plot, which is known as a density plot, towards the end of this lecture. So again, no worries if density plots are new to you. The idea here is just you plot your data along, the x-axis is your data's potential values, right? And then the y-axis represents the popularity of those values. So here, we're not seeing many observations taking on these values, and we're seeing no observations or very small enough that it's not even showing on the plot, observations at this level of x. And as x increases, so does the number of observations we see at those values. It peaks right here at the mean, median, and mode, the true center of this type of data, which we'll talk about in a little bit. And then it starts to become less frequent as you move to the right. And we'll talk about this in a little bit, but some of you might be familiar with this particular density as the bell curve because it's shaped like a bell. Some of you may even know that it's called the normal distribution. There are other distributions that have a bell curve shape, but in this particular case, I'm talking about the normal distribution, which we'll get to after we cover a couple other statistics. So we talked about 3 measures of center, and I want to know your opinion of the 3 that we talked about, which one is best. And I gave you a little image here that you might want to consider as you think through which of those 3 measures is best. So I am curious what your thoughts are. If you can share them in the comments, I'll read them and reply. And the answer is, as you might have guessed, there is no best measure of center. This is actually a really hotly debated topic in statistics. What is the best statistic? And it really depends. There's a lot of criteria used to evaluate statistics, and there's the definition of best will vary depending on the criteria you use. But like I alluded to in the first lecture, statistics is a bit of an art, and depending on what you're trying to communicate, you'll choose different measures of statistics. So one thing you may have heard in the past is when dealing with highly skewed data, which if you don't know what that means, that just means it's pulled in one direction. So this is skewed to the left. I actually don't like the word negatively in this image. I would say skewed left. And this is skewed to the right, or positively skewed is another way to say it. So with highly skewed data, there is a large difference between the mean and the median. And depending on what you're trying to communicate, you're going to choose one of those statistics. And I think most people are concerned with the median. So one example would be income, right? Income is highly skewed in this country and around the world. So if you really want to get a measure of center, The median is the measure at which half of people make less and half of people make more. So it's a much more accurate measure of center than the mean, or a much more accurate way to communicate the income you expect than the mean, which is going to be skewed by the handful of people with extraordinary amounts of wealth. And then as you can see, in the case of normal data, the debate about which of these measures of center is best is trivial because they all agree with each other anyway. So now we're going to talk a little bit about measures of spread, and we're going to start with ranges. There are other measures of spread you may be familiar with, but we're going to start with these two because they are simplest. Range is a word you've probably heard before in other contexts. Just what does my data span? So if you take your largest data value minus your smallest data value, that is the range of your data. So to go back to example A, right, the range here is 8 because our maximum is 9, our minimum is 1, and it spans, a distance of 8. The interquartile range, often referred to as the IQR, is quartile 3 minus quartile 1. What does that mean? Well, you might be familiar with the word quart. The root quart means 4. So if you split your data into 4 pieces, much like you do when finding the median, right? You split your data into 2 pieces. Well, now repeat. So first you find the median, now you separate your data into 2, then take each of those pieces, find the median again, and now you've separated your data into 4 pieces. So you take the quartile 3 minus quartile 1 to find the IQR, and I want you to think a little bit, and we're going to do an example in the homework where you calculate the IQR and in the quiz. So I'll give you that information now because I think it can be a little confusing. I want you to, for now though, before we get into the details of how to calculate it, I want you to think about why people might prefer the IQR over the range. So you might have used the term outlier in answering this question. A lot of times people will choose the IQR over the range to avoid undue influences from outliers. So for example, actually I don't have an example in these slides, but you could imagine, to use our prior example of income data, right, there are people who make billions of dollars a year, but the vast majority of people make several figures less than that. So the range is not giving you a ton of information. Like the data is very spread, but I want to know where the bulk of the data lies. And in that case, the IQR is going to be more helpful. And we'll talk more about outliers in the future, but these are just data points that are very far away from all the other data points. So let's do an example using these measures of spread. This is one way in which they're applied, is through a 5-number summary. And a box plot is really nothing but the 5-number summary visualized. So the 5-number summary really helps to summarize your data in a non-visual way, and then the box plot makes that visual. If you're familiar with R and you run summary on your data, what you get is the 5-number summary plus a couple other statistics, assuming your data is quantitative or numerical. So the 5-number summary is really simple. When I used to teach this in middle school and high school, we used the hand. First you want to grab your minimum, and then in order, the next statistic that you want to grab is your quartile 1, then your median, then quartile 3, and then your maximum. Let's talk a little more about those quartiles, like I said. Quartile 1, right? We talked about how you get the quartiles. You split your data in half to get the median, then you split each of those halves in half again to get each quartile. Quartile 1 is also sometimes referred to as the 25th percentile. They're exactly the same thing. Quartile 3, the 75th percentile, exactly the same thing. You might also see the word quantile, which is a little confusing, but quantile is just like another way of saying percentile. And JUMP actually does use quantile instead of percentile, so you will see that if you use JUMP for this first homework assignment. So now that you've got your 5-number summary, how do you visualize the range? Well, you make a box and whisker plot, and the easiest way to make this is just draw a little line at each of those statistics, which you could see labeled by those blue lines. And then the 3 in the middle, which make up your IQR, you're going to connect with boxes. And then the minimum and maximum, you're going to connect with whiskers, which is why this was initially called a box and whisker plot, now called the box plot for short. And this takes some getting used to. It's not like the easiest visualization to understand, but it does speak a little bit to the spread of the data. When I look at a box plot, I look at the boxes first. I know 50% of my data, specifically from the 25th percentile or quartile 1 to the 75th percentile or quartile 3, lies in there. I look at the line in the middle of the boxes. I know that's my median or measure of center. And then I look at the whiskers to determine the full range of the data. Although I should note, and you're going to see in an example in a future slide, the whiskers don't always go to the minimum and maximum. There is a rule that you don't need to know, but I'm going to let you know now anyway. It's just a rule of thumb. There's no mathematical justification for it, that any data that's more than 1.5 times the interquartile range, the median plus or minus 1.5 times the interquartile range is the highest you would ever mark the maximum on a box and whisker plot. And beyond that, you would mark them as individual data points or outliers, which you'll see in this slide here. So we'll get into what this is saying in a minute, but like you'll see, this is my true maximum, but my whisker doesn't extend there, because if I take this interquartile range, which seems to start at around 31 and end at around 42, so it's about 11, let's just say 10 to make the math easy. So if I go 15 points from my median, which is at around 35, will take me to around 50. This is where the whisker stops. If there's data at or exceeding that point, that's where you would stop the whisker. And then all your other data points that exceed that, you would mark with a dot, or in this case, an asterisk. That might be a little confusing. Don't worry, you don't need to know that. But I just want to explain to you that sometimes when you look at box plots or box and whisker plots, the whisker doesn't actually extend to the true maximum. It'll stop at what the interpreted maximum is. So here's a box plot. Take a minute to look at it, and I want you to think about what this plot is telling you. So to me, I think this is a pretty good plot in that it's simply labeled. They do repeat age both in the title and the axis, which may be a little redundant, but it's split by gender, so you're seeing two distributions. And it seems like men tend to be older than women when they win an Oscar, at least in this time period. And this is the qualification like we were talking about in Lecture 1, at least from 1975 to 2004. We don't want to extrapolate beyond that because we didn't use data beyond that. So it seems like men tend to be higher. Of course, there are exceptions. For example, all the men here, which is 25% of the data, were lower in age than all the females from this point forward. So there are exceptions. It's not always the case that men are older, but it tends to be, right? The minimum is higher, the quartile. In fact, all of the 5-number summary statistics are higher for men than for women. So that's kind of the one way to visualize. A lot of people are less comfortable with box plots. There's other ways you could show this besides a box plot to make the same point. Although box plots are very common in statistics. I want you to think about some of the other charts you might use to make this same point, that men tend to be older than women at the point at which they win an Oscar during this time span. So like some other options are overlying density plots or histograms. I know we haven't talked about those yet, but those are other plots to show the distribution and spread of your data. So that's another option to make the same point. So now let's talk about standard deviation. So this is a measure of spread I left to the end. I think range and IQR are easier to calculate. There's a lot of mathematical notation here, which makes it seem more complicated than it is. But if you break down the words, standard is kind of like the expected amount of deviation. Deviation is just like how much your data varies. And I know a lot of people are turned off by mathematical notation, but these formulas are basically the same. I want to talk about those differences in a bit. I want you to think about them first, though. But the idea behind standard deviation is it's a calculation to get at how much your data varies. And you can see each of these mathematical symbols is explained below. And just like before with mean, we use a different notation when we're talking about the sample standard deviation as opposed to the population standard deviation. This is the Greek letter sigma, lowercase sigma, and this is S for sample standard deviation. And the formulas are very similar. There is a difference, and we're going to talk about that difference too. Before we get into that, I want to ask you, if you're familiar with variance, what is the difference between standard deviation and variance? And why do you think I'm presenting to you standard deviation as opposed to variance? So variance is almost redundant. There are reasons we use variance instead of standard deviation. It has certain mathematical properties that make it more useful in certain applications and proofs, but it's the same thing as standard deviation, just square it. And you look at these formulas and you realize, well, I'm taking the square root. So variance is just simply removing the square root, right? Because if you square something inside the square root, you just get the thing that was inside the square root. So in a way, the formula is simpler. You just take the square root away and you get your variance, and you'd add a little square here to make it clear that you're talking about variance. The symbol for variance is the same as the symbol for standard deviation. You just add that little exponent. So why am I teaching standard deviation? It's a little more complicated. It's got that square root. What do you think? What are your thoughts? So the reason I'm teaching standard deviation, and it's not the most intuitive thing, I would be very impressed if you figured it out, is just that the units are on the same scale as my data. So like you see here, X is my data, right? And this we talked about is the population mean. This is the sample mean. And then I divide by the count of either the population or my sample data minus 1. And because I'm squaring these differences, right? Let's say I had a data set on heights, and the average height in my data set was 5'6", right? Let's make it easy and say 5. No, I did say 5'6". So 5.5 as a decimal, right? Because 6 inches is half a foot. So I'm taking all my heights in feet, subtracting 5.5, and that gives me something in feet, but then I square it, so now I have feet squared, and then I divide it by a count, which doesn't have units. So variance, if I'm collecting heights, would be in feet squared, which isn't quite as interpretable as feet. Square feet is used in other contexts and other applications, but it doesn't really make sense when I'm talking about heights. So that's the benefit of standard deviation, is just the units are more readily interpretable than with variance. And there are other ways to get at deviation. There's also mean absolute deviation you may be familiar with. If you're not, don't worry about it. But this is by far the most common in statistics, especially in introductory classes. So lastly, I want to talk about the differences between the sample standard deviation and the population standard deviation. So, obviously you notice these two symbols, mathematical symbols, are different, and we talked about those differences, right? This is the population parameter, and this is the sample statistic. What about the denominators, though? Here, I'm subtracting by the count minus 1, or I'm dividing by the count minus 1, and here I'm dividing by the count. Why is that the case? And this is another thing that I would be really impressed if you knew, but it's not something you're going to know unless you've taken a statistics class before. But the reason is essentially you lose one observation in estimating the mean, because this is the sample mean, not the true mean. And so you lose one observation in doing that. That's kind of an intuitive explanation. It's actually a little more complicated than that. But it is important to note, and I do want to highlight to you, that the formula for sample standard deviation has this minus 1, which is absent when you know the true mean. Okay, so we talked about application for ranges previously. What's the application for standard deviation? It's more complicated than the IQR. It's a little more work to calculate, although nowadays with computers it doesn't take much. We talked about the application with the IQR and the range is you can make a box plot, which is a nice visualization of spread. It's often used. What's the application with standard deviation? And there's really one main one with a huge caveat that's often ignored that I'm going to talk about. So you might have heard of the empirical rule. No worries if not, but the empirical rule just says that for normally distributed data, and that part's really important, and we're going to emphasize that again later, these are the percentages of data that lie within 1 standard deviation, 2 standard deviations, and 3 standard deviations. And again, I know this notation might be a little intimidating for people who haven't seen it before, but remember, mu is just my population parameter, and sigma is my population standard deviation. So mu plus or minus sigma is this range. That should cover 68% of my data. Mu plus or minus 2 sigma, that's this range by the blue line, should include 95% of my data. And then plus or minus 3 sigma would cover 99.7% of my data. So why do we have this rule? Well, it's one way to make sense of the standard deviation and apply it, is I know for those ranges I can get at 68%, 95%, 99.7% of my data by adding and subtracting 1, 2, and 3 standard deviations respectively. Now I want to talk a little more about that caveat because I think this rule is often applied in cases when it shouldn't be. So this empirical rule, as it's called, you might also hear it called the 68, 95, 99.7 rule, which is kind of a nice way to call it because it gives you those percentages that the empirical rule is getting at. It only applies to normal data. There are other rules for data that's not normally distributed, but we're not going to cover those in this class. And obviously they're less powerful. So when you know the distribution, you know a lot more about how much data lies within these points. Okay, so given this caveat that the empirical rule of using standard deviations to figure out how much of your data lies within certain ranges only applies to normal distributions. Given that caveat, let's talk a little bit about what normal distributions are. So again, there's some synonyms here. Some people call it a bell curve, which is a little misleading because there are other distributions that have a bell curve shape. A lot of people call it Gaussian. Same thing. The reason it has that word normal is because it occurs somewhat naturally when you're measuring data. For example, heights are normally distributed. So if you were to just collect a bunch of heights randomly and representatively from a population of humans or another animal, it's very likely that when you make the density plot, it's going to look normal. And a lot of other things in nature are assumed to be normal. The reason there's so much focus on the normal distribution, though, is because the sample mean is assumed to be normal regardless of whether or not the initial data was normal. I'll talk a little bit more about what I mean about that. So like income, we talked about before, is not normal. It's heavily skewed, right? It's not symmetrical, it's not bell-shaped, it's not even on both sides, right? There's much more mass towards the left side of that distribution than on the right side. However, if I were to take the average salary from that distribution and then collect another sample, take the average of that sample, and then collect another sample, take the average of that sample, and repeat that process many, many times, those averages would be normally distributed. And that's what this is known as the central limit theorem. So regardless of the data you start with, if you calculate the sample mean over and over again many, many times, those sample means will be normally distributed provided that I do it enough times. So that's one reason we emphasize the normal distribution. The mean, as you might have expected, is a really popular statistic, so knowing its distribution is helpful. Again, it's not always normal. You have to have a high enough sample size. But this is a very common popular rule in statistics known as the central limit theorem, that the mean will be normally distributed if you repeat that process over and over again. And a rule of thumb, again, this is just a rule of thumb. There's no math to justify it. And actually, what it really depends on is how normal your data was to begin with. Because if you're starting with normal data and you take many samples and take the mean of those samples, you don't need a high sample size to achieve normality for the means. However, if your data is far from normal, you better have a lot of samples. And the rule of thumb is 30 samples. Why 30? I couldn't tell you. Actually, I do think I know why it's 30. It's because there's a distribution that we will cover later in this class known as the t-distribution that approaches the normal distribution when your sample size is 30 or larger. However, like I said before, it really depends on what your data looked like to start. But the rule of thumb is 30 for better and worse. So let's talk about the standard normal distribution now. We talked about the normal distribution. I want to talk about the standard normal distribution. So this is a normal distribution. This is also a normal distribution, but this one is called standard, and I want to talk about why. So when you look at the x-axis of this distribution, we see that it's centered at 1010 and it's spaced out, it looks like 20 units on the axis. That doesn't really say a whole lot about the distribution, but on the axis. So what's the difference you see between this and the normal distribution? I'm sorry, I should have said what's the difference that you see between a normal distribution and the standard normal distribution. And the main difference is where it's centered. So in a standard normal, you want it to be centered at 0. Similarly, the spacing or standard deviation should be 1 unit. That's the difference between every other normal distribution and the standard normal, is just what's the center, what's the standard deviation. For a standard normal, it has to be 0 with a unit of 1, with a standard deviation of 1. And how did they come up with 0 and 1? Why do we use those numbers? I want you to think about that for a minute, and then I'll tell you. Well, as you can imagine, right, these are like easy numbers to work with. And it's easy to convert a normal distribution to a standard normal distribution, knowing that that's your end goal. But why didn't they make the standard deviation 0, right? 0 is an easier number to work with than 1, generally speaking. Well, that doesn't really make sense to have a standard deviation of 0. It would mean all your data points were exactly the same. So we use 1. And the way I want you to think now, how you would take a distribution you know to be normal, like heights, and convert it to a standard normal, knowing that you want the mean to be 0 and the standard deviation to be 1. So how would you go about doing that? So start with the first part. You want the new mean of the standardized normal to be 0. It's pretty easy. Take the current mean and subtract it from all your data points. Your new mean will now be 0. How do you change the standard deviation from whatever you started with to 1? That's a little trickier, but the idea there would be just to divide all of your data points by their standard deviation. So here, they subtracted 10, 10 from each data point, and then here they get 0. Here would have been negative 20, negative 40, negative 60, 20, 40, 60, and so on. But we want the standard normal, so then they just divided everything by 20. And now we got the standard normal. So that's exactly how you standardize. If you forgot, here's a handy formula. It's this simple. And I know you're wondering what that letter Z is about. I'll talk about it in a minute. But you take your data, which is typically represented with X, sometimes Y. You subtract its true population mean and divide by its true population standard deviation. And then you'll wind up with a standard normal. That letter Z is just traditionally what is used to refer to the standard normal. That's all that letter means. You might even hear people call it the Z distribution instead of the standard normal distribution. Okay, so that's a little bit about the descriptive statistics. To review what we covered, we went over a few measures of center, and different scenarios you might want to use each of mean, median, and mode. We talked about measures of spread and when you might want to use the IQR or the range. And then we applied the IQR and the range to the 5-number summary and box plot. You'll be doing the former in your homework. And then lastly, we covered standard deviation, which you will apply to with the empirical rule if your data is normally distributed, which is a big if. It's not always the case, so just be mindful of that when you're applying the empirical rule. And I will send over a few homework assignments, probably the next homework, involving those concepts. Thank you.